Hey. Hello. Hello.
Sure. There it is.
Hello.
Hey.
Everybody.
Hi. Hi. Well, so I heard David is starting their own Slack channel, which was we had talked about it. It's a good idea. Just anything in that text things. I mean, within a few days, whatever you enter in the Slack channel gets wiped out because it's got a limit of 10,000 messages for a free group. So.
I'm just going to push this off the table. Oh.
Have we talked about anything yet? Have we gone to, are we watching the video, at least start and stopping it and stuff? People have some questions or?
Do you remember what YouTube shows we were looking at together? We talked about this 2 weeks ago, but we don't remember anything anymore.
This is just.
Remember we talked about one of that deep learning lesson, we would watch it and then come and discuss it here?
I thought we'd watch it together, all together, and then stop.
Or something, start and stop and at least say, yeah.
Yeah.
Because that's what we were going to alternate. Hey, 1 week we're going to do that and the next week there'll be some presentation and stuff like that. So
I guess we could start with part 2, the first one maybe. This is a specific video.
Do we have a specific part we want to watch though? It's a long video.
I mean, we had to finish the whole thing today, or like parts?
Well, I mean, I don't think we even have time to finish the whole thing.
Yeah.
Parts is fine.
Yeah, we can just start and then stop.
You're not now.
And then we can discuss other stuff.
Because they give the timeline.
Everybody's gonna
On Fast AI, like they give the breakdown of like what he talks about where, so we could just pick something
what is the privilege?
that we think is.
oh yeah, there is the time thing, time stamped and stuff, and what he's talking at each of the time stamp, and we can go there automatically rather than start from the video.
Yeah, I think that might be the best way to go about it.
Set the
Just
picture.
pick a timestamp that seems the most relevant to us.
Yeah. And which one which one we were going to talk about? The sequence or the GAN or?
Are you looking at it on your screen right now?
Yeah, can you share your
Yeah, I'm looking at it on my screen. I can, yeah.
Can you share your screen?
Okay, let me share my screen. Yeah, I mean, there's,
Yeah, the first one's object detection.
yeah, object detection. Yeah, I mean, trying to put a thing, yeah, trying to put a box around the object. I mean, that's there. I mean, people really want to now detect object, like, I mean, not just put the box around. I mean, the masking is more useful. I mean, trying to pixel by pixel the image segmentation rather than just put a box on it. But I mean, but everybody is doing the box. I mean, that's what all the commercial stuff, AWS, I mean, the deep lens, that's what it does, is puts a box on it and says what it is. And all the other people, everybody, AWS's Rekognition or Azure's thing, they all have a package out there that will recognize the, put a box around and say what it is. I mean, that's actually 2 lessons. I mean, the box thing, object detection, is actually 2 lessons, trying to get that correct, because the first lesson he only does a box on the majority class. Then he says, okay, how do I do multi-box and multi-object detection? The other one is NLP classification and transfer learning. I mean, again, those are two classes together. I mean, he starts with what is the classification, and he trains a model, and then how is he going to use that for training another model? So, I mean, they are pretty, I mean, from an NLP point of view, pretty interesting. And then he gets into, I mean, initially he only does NLP classification. I mean, I think it's sentiment classification. And then he gets onto the translation, how to do translation using a sequence-to-sequence RNN network. Pretty interesting stuff from that. I mean, anything on NLP, you would want to watch those 2 videos on NLP. And this image-to-image translation, yeah, they're using the adversarial networks to do the image-to-image translation. And then he goes on to a little bit more on style transfer, image-to-image translation, yeah, the Monedo things, and then the style transfer is there, which is just a continuation of that. And then he talks about data ethics for at least half an hour in that. And then there's Carvana, which we all know about. So which ones do we want to talk about?
It's all good.
Yeah, they're
Pick
all
one.
interesting. Personally, I don't know. I haven't done a whole lot of NLP. At some point, I'd like to get into that more. But,
Did you ever get to learn more about your time series stuff?
Yeah, actually, yeah, I made progress.
Just what did you find a good,
Wait.
learning experience? Sorry,
It's coming back.
I'll touch you that. I'll touch you that. Yeah, I don't know where he gets. I've actually watched the first.
I've done like the opposite. I've watched 10, but I haven't seen 8 or 9.
The 2018. The 2018.
Yeah. That was cool. Like I went through one of the notebooks with them. We went through, did like a thing with Twitter.
Do you want to vote or something?
So Yeah, all right. Do you want to just do like a show of hands for 8, show of hands for 10? All right.
What's it?
Box.
Yes. 8 and 9 are out. So who wants to learn how to take section?
I do.
Okay.
Echoing quite a bit.
Yeah.
Somebody else?
Oh wait,
She
what do
does.
we? Okay.
Jesus, she isn't trying.
Wait, did we tie?
No, it's 3-2 so far. Did you vote?
Yeah.
NLP?
Exactly.
You can.
You voted NLP?
Yeah.
No, it's 4-2.
Oh, yeah.
All right.
Just mute.
So I think
Yeah.
here we voted for lesson 10. Is that okay with you?
Yeah, lesson 10 is fine. The NLP stuff.
How many people?
Yeah, lesson 10, you start off with the NLP thing. Yeah. Let me go to where the lesson wiki. That's where they have the timelines and stuff on that.
All right.
And in the beginning is a review of the other lessons. Skip that and stuff.
Yeah, this one, I didn't know about this, and he talks about this panda's chunk size to deal with a large corpus. That was interesting to me. This chunk size thing I haven't used before. So it's kind of, I think it's like a batching thing that pandas does, but I'm forgetting now what exactly.
Yeah, if I remember correctly, I think he just spends most of the time running straight down the notebook. Yeah, it's like, how far is too far to just jump in and still know what's going on?
I thought Narayana was going to show us all this cool new stuff that he's done on the competition.
Oh, well, I mean, I can talk about that. I mean, finally, I got about 0.8. I got to about 0.80 6 or 7 or something like that. And then I stopped because initial goal was 0.8. I wanted to get about 0.8. And and then I wrote a Kaggle discussion thing on that.
Yeah, you said you had like the highest rated Kaggle kernel?
No.
No, not a kernel. This is a discussion.
Oh, a discussion.
Yeah.
I thought you meant a kernel.
He was just the most controversial.
No, I haven't submitted my thing. I haven't submitted my, so this guy actually went from 0.78. He's got now more, 86. I had 86 votes on my thing, my painful climb to LB. So he's got some notes on how to go from 0.878 to 0.84 plus. But I had actually a much better thing of,
Because you have the same number of comments as he does.
Just
Yeah, I just need to upvote it once.
yeah. So he talks about ways I have to try. I haven't done anything last week. After I got the 0.8, I just quit. I mean, it was just getting like a big addictive game. I would do this, I do that, and I keep on going. So then once I got to 0.8, it looks like going to 0.84. All these guys have used, instead of 128 by 128 image, they've used a 224 by 224 image on the ResNet, on the pre-trained ResNet. So what they've done is they have taken the 101 by 101 image and then resized it to, I think, twice that, which would be 202 by 202, and then did a reflection padding on that to get to 224. And that may, looks like, I see even the guy who has the seventh position on the leaderboard, he's used a bigger size image and stuff. That I don't know why. Because ResNet was optimized on a bigger size image. Maybe it does better with the bigger size image than a smaller size image. So I'm gonna start training my model on that. The other thing, the big thing to even get above 0.8 was to use the loss function called LOAS loss. And everybody has done the similar thing, is you use the binary cross entropy loss initially, and then they use a LOAS loss, and this is based on one of the papers here. The LOAS softmax loss, a tractable surrogate for the optimization of the IOU, because that's what we are doing here, the intersection over union measure in neural networks. I haven't gone through the paper to understand what exactly it's doing. That's something I need to do. And then the other, the LOAS hinge and the LOAS softmax for the, they talk about a LOAS hinge and a LOAS softmax for the Jacquard index. So the LOAS hinge, he gives an implementation of this LOAS hinge there. If you go for a binary demo, and it seems
Can you paste this repository in the Slack room?
oh, this one, this LOAS last thing.
Yeah.
Okay.
I'm having a hard time reading it from the screen here.
I'll do that. Let me, where's the, that just had the, I thought he had a, oh yeah, LOAS losses.py. That's the main thing. That's where he's documenting was LOAS losses. I haven't gone through to even understand what it is. All I did was just copy and paste that and use that loss function. And it seemed to train, I mean, it seemed to lower the loss or it seemed to improve the IOU metric as it trained. But you can't just start training with the LOAS loss because it doesn't learn fast enough so you train with the BCE loss for some time, binary cross entropy, and then for say 30, 40 epochs, and then switch it over to the LOAS, this LOAS hinge loss. And the other thing they've done, I've seen, is, what is it? Or they also talk about a binary cross entropy plus dice loss. Instead of just using the binary cross entropy only, they're using the sum of those two losses, the dice loss and the binary cross entropy loss, while running there. The other thing is also I just used the FastAI's UNet. Some of these higher ranked people, they've designed their own units. So I need to go and design based on their architecture, make sure I can, just do that so that to replicate their architecture rather than just use the FastAI's unit architecture. And I didn't see anything really, what is it? All he said was the, unit with the, it's actually 34, not 32. And then the SGD optimizer learning rate, you start with this 30 epochs. So he got whatever, this is what I would get, like 0.775 and 0.769 and all that stuff. And then what they also do is they do a this guy has done a 4-fold, or you do a 5-fold. What they do is they splice the data into 5. It's different from the traditional the cross-validation fold and machine learning. So what they do is they slice it off, and then they take 5 different combinations of the data. Basically, they're saying four sets of data is training, and then the 1 set of data is for validation. And so they train 5 different models using 5 different combinations of this these 5 buckets. And then that, they say, improves their thing. Even here you see here, for each of the folds, he gets 0.769, 0.784, 0.775, 0.763. Once he puts averages all the 4 folds and does the PTA, that score jumps to 0.797, which is higher than any of these individual scores. Then what is unbelievable, all he said was, hey, I just took one of the folds and then he reduced the learning rate and then the focal loss. He used a focal loss. They also use a focal loss instead of a binary cross entropy loss. I haven't used that. And then he just changed the focal loss to Lovász SC loss, which I showed you, and then train 85 more epochs and then reduce the training rate by another half after that. And then he was able to get just with a single fold and a flip PTA of 0.832. But he also used a 224 by 224. So I'm trying to, I'm going to do is, I'm going to try to replicate his methodology. I already know I've done all this stuff. I just need to replicate his methodology to see what I can, increase the H to 224 by 224 image, and then also use this UNet based on whatever people have told about the architecture, just redefine that UNet from FastAI on my own, and then see where I can get, if I can easily get to 0.832. And then he says for the fine-tune number 2, he froze the batch norm layers of the ResNet 30. It's a 34. Starting weights was the best checkpoint, and then the Lovász loss, and then he did that. He trained it for 60 more epochs, and he got to 0.841, he says. So it looks like it's just a few things that need to be changed. And he used the similar augmentation we're talking about, the horizontal flip, a little bit of brightness, a little bit of rotation, and also this random crop and resizing augmentation. And he is on the 26th place right now, which means he's actually has even higher than this point. Whatever he talked about it here, he also has it higher than the 0.841. Obviously, once you get to this, you can do the what David had suggested was, classify the images as no mask, use the classification algorithm, and then the regular thing, and then that should boost the score also. And people talk about that, how that boosts the score. And he's also talking about, so 841, if I look at Peter on the leaderboard, he's 26th place. Yeah, when I got to 0.805, I was under like 215 or 230 or something. I was in the bronze. Right now, I'm not. I mean, you have to work on it every day almost. Looks like it. What position was he on? 26th. And this guy, this 15, this Henk Cherken, he blocks quite a bit, and he was in the 7th place for a very long time, and he has already fallen to the 15th place. 46th, or what did I'm forgetting, 26th place. So the 26th place is not Pesti, it says. I don't know why it says Peter, 26th place. Oh, it is Peter. Okay, his name. So he's gone to 0.851. So that's what he's talked about. Hey, if I do the ensemble 4 folds, so the 841 went to 0.85. Basically, looks like it. So those are the idea. I mean, I didn't see any more. I mean, people are trying stuff, and he even shared how much his loss was, the validation loss. I just need to check if I'm getting same. And also he was modified Lovász SC. One of the things, I didn't modify that, so I have to try that. One of the things they mentioned was this SC has an F dot, not that place. Where is it? Not that one. Where is the lowest multi-class loss? Where there was a place where let me check. There's only one ReLU. I didn't think there was just because they talk about, instead of using a ReLU, they talk about ELU plus 1. So I'm trying to see, there was an ELU plus 1 there. Lowest hinge flat, hinge. I forget where it was now. Because this is the binary loss thing that you do the hinge loss on it. Prediction. So there's a place to change it instead of ReLU to ELU. So softmax, he does that. Lowest hinge training, figure, final prediction, binary cross entropy training. He just compares it with the prediction. There's a place, now I forget it completely where it changes it from. Nope, it's not there here. It's got to be here. Otherwise, I mean, it's not the f.ReLU. There was a place where he talked, I mean, that's why he's talking about that. Use ELU instead of ReLU. Okay. So maybe instead of f.ReLU, they use a ELU, f.ELU plus 1 here, and that they say is more stable than using the ReLU here. This is the lowest hinge loss, which goes to the hinge flat here, and I suppose somewhere here we saw the f.ReLU, f.ReLU. So they're saying instead of using the ReLU, use a f.ELU plus 1 here. And I saw some places where they talk about that instead of ELU plus 1 instead of ReLU. Okay, is that a leaky? Okay. Yeah, this is the guy, I think he had some graph or something. Yeah, he says his ELU is very similar to ReLU except negative inputs. They have both an identity function for non-negative inputs. ELU becomes smooth slowly until its output equals to minus alpha, whereas ReLU sharply smooths. Notice that alpha is equal to plus 1 in the following, because ReLU would go to 0 here, and then they're saying ELU would go like this. And then they're adding plus 1 to come back to something similar to what ReLU would do. But then if you add 1 here, it's probably going to be shifted by 1, and then going to be somewhere, it'll be positive, but it'll be it will reach the 0 slowly rather than just becoming 0 right here. So I have to dig through and see what it means and how why this is more stable. So that was that on this. And he shared what he did and what his accuracy training was. So I'm going to replicate that and see where he is. And then if I can get 0.834, I'll blog again on that. So 0.85 or something like that. a lot of things. I mean, but it was a good thing to learn a lot of things on this competition. Okay, I mean, how do you do the cross validation setup? I mean, what kind of argumentation works, and then, I mean, this image size is becoming a thing. I mean, does increasing the image size train better? I'll see if that happens. And then using different loss functions, using one loss function initially, and then training with a different loss function later on. So those are things, I mean, I think like FastAI didn't cover those kind of things, and it's good to learn those things in a Kaggle competition. Other than that, I was looking at that thing, is this guy, yeah, okay, this guy used to be Pude, he used to be #1, he's been, this guy somehow come from, yeah, just 50 something, he's gone up top. I mean, he's climbed 30 positions. So he must have had a big jump in his algorithm to go from 30 to #1. And as they say, what is the prediction is, the winning score will be close to 0.9 as people experiment and experiment and experiment, be close to 0.9. And then the bronze, you would need about 0.83 or 0.84 to have the bronze on this thing. So that's what I got. I mean, it's just, gosh, it feels, I mean, I'll see, I have fallen 134 things because I didn't try anything. So to keep trying to keep my position. So otherwise you won't get it. I mean, just in a week, I left off because I had to travel to this conference and stuff. I've fallen 134 positions.
Well, plus you told everybody what you did.
Yeah, plus I told everybody, yeah, could be.
Yeah. So they all did it the same thing with just a little bit more training.
Yeah, a little bit more training, but at least the other guy has posted, so I can't complain too much. There are guys with 0.84, 0.85 posting, so they're sharing that, and so I'll be able to jump into that pretty soon. Oh, okay, you uploaded my thing.
Yeah, I upvoted you.
Okay, cool. So I would have at least I'll have a little bit higher competitive sex.
All right, I think we should finish up with watching the video. I just didn't want to miss out on the opportunity for you to talk if we got into the video and then lost track of time or whatever.
Oh yeah, we lost track. I mean, then I'm planning to gear up again this weekend to test a few things. And then I was working on something else this weekend. Even I was up at 2:30 a.m. working on some JavaScript coding and stuff like that. So I need to get back on this. But I also wanted to wait for before other people would post, and I can learn from that before I started doing more thing. And as I told in the Slack channel, I met a Microsoft guy who's working. I mean, he works in this. I think their ML Azure platform, and he said, "Well, if you're willing to blog what you did." I mean, there is no guarantee. He just said, I'll give you a month free of GPU. You can do whatever you want, just as a good gesture. If you can just blog about your experiences with the tool and stuff, I'll be happy about it. So I said, okay, I'll ping you when I'm ready to start my deep learning again, and that'll be good. Because whatever I did on Paperspace, just a few hours. I mean, that just ramped it up. I mean, I was trying to pay Paperspace before I gave up on it, but that itself, bill me $5 for just that. I mean, you just don't realize how easy it is to keep training and lose track of how many hours you have spent on something. I mean, that means like 5 hours means I've spent because it's only 50 cents, I've spent 10 hours on it. So even though it didn't look like it, but that's what it is. What else? Oh, the other thing, and we'll talk more maybe next week and stuff when I can be there and talk about a few things. I'll show you some slides from from the conference, some tutorial stuff that I took and stuff. It's pretty cool. I'll show you a Microsoft project that I took a tutorial on, a half-day session where they are trying to do what this image segmentation we are doing with the mask, with this thing. They're trying to do it with the diseases. I mean, they have all these X-ray images, and they're trying to they're trying to identify what's the disease and trying to mask the disease, the disease area or the organ where the disease is and stuff like that. And he showed things. In fact, they didn't use deep learning. They used something called a deep random forest. So. And I have to check but they said it is easier to train and things with the deep random forest. I have to go back and read through what a deep random forest means.
Yeah.
They use deep random forests. We saw a guy give a talk about deep random forests.
Oh.
A couple of months ago.
Yeah,
it was like this guy's like PhD thesis out of like somewhere in China.
Kid, yeah.
And like the guy was not even into deep learning in any other way, but he liked this paper, and so he gave a talk about it. Yeah.
So what is?
Oh, gave a talk at one of the meetups.
I can't. Without, yeah.
I don't remember the details of what it.
Yeah, I mean, I have the paper on my.
Those shared all the GitHub and everything is available. I'll share it with the group next week when I'm there, and we can go through. I'll just show you what are all the stuff that they are done, and what they do is, and then they have what they've also done is Microsoft the latest Windows version. If you update to the latest Windows version, it comes with a tool called Windows ML. So, which means now once you have trained a model, they showed, okay, now if you have Visual Studio, they had some skeleton code. They said, now you just throw the model here and they showed how easy it is to build. I mean, since they don't have any a phone system now, I mean, Windows Phone has died. So they said you can easily push it on iOS or Android. And then he showed right there how he was doing that, and he was just executing some code on his Visual Studio. He shared everything. It was pretty interesting. I mean, we still have to. That session was not like we didn't work on it. He was more showing, okay, here's what I did, here's what I did, and he shared all the GitHub and everything. We just have to work through it and see, okay, how useful is this? I mean, the results look pretty good. And he had an iPad, and he said, now I ported this to the iPad, and he got it, and he took an X-ray thing, and then he just flashed his camera on the X-ray, and then I just told him, okay, what is the probability of the disease that is detected, and it's also masked the disease area. And they called it saying, hey, this is going to be very useful in the developing world where they don't have access to radiologists quickly, at least, and they said in the US it will help the current radiologists go through a lot of their work if the computer can at least identify, do some pre-work for them, and then they can look at it and say whether they agree on it or add their own annotation on it. So. I'll share. I mean, that's a longer conversation. I mean, those two, and then the other one I also will share is what they talked about. One of the
Disconnected.
I think we lost you, Narayan.
Challenges, and then having to show what data was used and what data was used in training, and what was the validation data. All that stuff is going to be needed in a subpoena environment. So, and they had a few tools how data versioning happens, and that was pretty interesting because I mean we all know code versioning through diffs and stuff on GitHub, but data versioning was very interesting. So, okay, that's all I have.
All right, who wants to play the video? Eric?
Yeah, I can play it since we're on this.
Oh, before we start, who is presenting next week? Anybody, or are we doing this again?
As I said, I can
to-
present next
usually
week.
one of us presented.
Yeah, as I said, I'll present something.
That was
for
fun.
you next week.
She can present.
If you want, I can present. I don't know if it's an hour's worth of material or not, but I can present I essentially repurposed his lesson 10 notebook to do sentiment analysis of just like
Okay.
popular figures on Twitter. So like who's the most like positive and negative tweeter.
Sounds good.
I can do that for a little bit.
That's cool.
No promises
That'd be
on
cool.
how much time that'll take up.
All right.
Okay.
So where are we going to start? Are we going to start at the beginning, or where are we going to start?
Which video are you watching eventually? What do we decide on?
We can do, or do you guys want to do 8, since I'll essentially just be rehashing 10 next week then I'm presenting.
You do 10 then, because
Or we can do 10 and then
Yeah, no, I think it's a good lead-in to yours.
Get it into
Okay.
your video cut off.
All right. So where do we want to hop in on this? So I think for this portion, he just goes through some of like the pre-processing steps for the movie review data. And then he talks about kind of the pre-trained wiki model. Yeah. Yeah, I don't really know where it's going to make the most sense to start. Do you guys want to know the pre-processing stuff he does?
Sure, I think we got about 45 minutes, so.
Okay. So yeah, that should put us about to here. Which, yeah, that's probably a good jumping off point.
So today we're going to look at the same idea and say like, okay, well, how does that apply to NLP? And then in the next lesson, we're going to go further and say like, well, if NLP and computer vision kind of let you do the same basic idea.
Yeah, if somebody wants me to stop at any point, just yell at me and I'll stop the video if we want to talk about something.
Is how do we combine the two? And we're going to learn about a model that can actually learn to find word structures from images, or images from word structures, or images from images. And that will form the basis, if you wanted to go further, of doing things like going from an image to a sentence, image caption, or going from a sentence to an image, which we'll kind of start to do phrased image. And so from there, we're going to go deeper then into computer vision to think about like, okay, what other kinds of things we can do with this idea of pre-training across the customer. And so we'll look at various kinds of image enhancement, like increasing the resolution of a low-res photo to guess what was missing, or adding artistic filters on top of photos, or changing photos of horses into photos of zebras, and stuff like that. And then finally, that's going to bring us all the way back to bounding boxes again. Okay? And so to get there, we're going to first of all learn about segmentation, which is not just figuring out where a bounding box is, but figuring out what every single pixel in an image is part of. So this pixel is part of the person, this pixel is part of the car. And then we're going to use that idea, particularly an idea called UNet, and it turns out that this idea of UNet, we can apply to bounding boxes, where it's called feature pyramids. Everything has to have a different name, slightly different area. And we'll use that to hopefully get some better results, some really good results actually. The bounding boxes. That's kind of our path to be. So it's all going to kind of build on each other, but take us into lots of different areas. Now for NLP last part, we relied on a pretty great library for torch text. But as pretty great as it was, I've since then found the limitations of it too problematic to keep using it. As a lot of you complained on the forums, it's pretty damn slow. Partly that's because it's not doing parallel processing, and partly it's because it doesn't remember what we did last time and it does it all over again from scratch. And then it's kind of hard to do fairly simple things, like a lot of you were trying to get into the toxic comment competition on Kaggle, which was a multi-label problem, and trying to do that with torch text. I eventually got it working, but it took me like a week, hacking away, just kind of ridiculous. So to fix all these problems, we've created a new one called FastAI.txt. FastAI.txt is a replacement for the combination of torch text and FastAI.nlp. Okay? So don't use FastAI.nlp anymore. Okay, that's obsolete. It's slower, it's more confusing, it's less good in every way, right? But there's a lot of overlays. Okay, like intentionally, a lot of the classes have the same names, a lot of the functions have the same names, but this is the non-torch text version. Okay. Okay, so we're going to work with IMDb. Right? So for those of you who've forgotten, go back and check out lesson 4. But basically, this is a data set of movie reviews, and you remember we used it to find out whether we might enjoy Zombiegeddon or not, and we thought probably my kind of thing. So we're going to use the same data set, and by default, it calls itself SQL IMDb, so this is just the raw data set that you can download. And as you can see, I'm doing from FastAI.txt import start. There's no torch text, and I'm not using FastAI.nlp. I'm going to use PathLib as per usual. We're going to learn about what these tags are. So you might remember the basic path for NLP is that we have to take sentences and turn them into numbers. And there's a couple of steps to get there. Okay. So at the moment, somewhat intentionally, FastAI.txt doesn't provide that many helper functions. It's really designed more to let you handle things in a fairly flexible way. Right? So as you can see here, I wrote something called getTexts, which goes through each thing in classes. And these are the 3 classes that they have in IMDb. Negative, positive, and then there's another folder of unsupervised. That's stuff they haven't gotten around to labeling. So I'm just going to call that class now. And so I just go through each one of those classes, and then I just find every file in that folder with that name, and I open it up and read it, and chuck it into the end of this array. Okay? And as you can see, with PathLib, it's sort of easy to grab stuff in, and then the label is just whatever class I'm okay. Right? So I'll go ahead and I'll do that for the train bit, and I'll go ahead and I'll do that test. So there's 70,000 in train, 25,000 in test. So 50,000 of the train ones are unsupervised. We won't actually be able to use them when we get to classification. Okay. So I actually find this much easier than the kind of torch text approach of having lots of layers and wrappers and stuff, because in the end, reading text files is not that hard. Okay, one thing that's always a good idea is to sort things randomly. It's useful to know this simple trick for sorting things randomly, particularly when you've got multiple things you have to sort the same way, in this case you've got labels and texts. np.random.permutation, if you give it an integer, it gives you a random list from 0 up to, or not including the number you give it, in some random order. And so you can then just pass that in as a indexer, right, to give you a list that's sorted in that random order. So in this case, it's going to sort train texts and train labels in the same random way. Okay, so it's a useful little idiom to use. So now I've got my texts and my labels sorted. I can go ahead and create a data frame from them. Why am I doing this? Well, the reason I'm doing this is because there is a somewhat standard approach starting to appear for text classification data sets, which is to have your training set as a CSV file with the labels first and the text of the NLP document second. Train.csv, test.csv, so basically it looks like this, labels and texts, and then a file called classes.txt, which just lists the classes. I say somewhat standard. It's just in a reasonably recent academic paper, Jan McClone and a team of researchers looked at quite a few data sets, and they use this format for all of them. And so that's what I've started using as well for my recent paper. So what I've done is you'll find that this notebook, if you put your data into this format, the whole notebook will work every time. Right? So rather than having different classes or formats and readers and writers and whatever, I just said, let's just pick a standard format, and your job, your code, so you do well is to put it in that format, which is the CSV file. Okay. The CSV files have no header, okay, by default. All right, now you'll notice at the start here that I have two different paths. One was the classification path, one was the language model path. In NLP, you'll see LM all the time. LM means language model. So the classification path is going to contain the information that we're going to use to create a sentiment analysis model. The language model path is going to contain the information we need to create a language model. So they're a little bit different. One thing that's different is that when we create the train.csv in the classification path, we remove everything that has a label of 2, because label of 2 is unsupervised. Okay, so we remove the unsupervised data from the classifier, can't use it. So that means this is going to have actually 25,000 positive, 25,000 negative. The second difference is the labels. For the classification path, the labels are the actual labels. But for the language model, there are no labels. So we just use a bunch of zeros. And that just makes it a little bit easier because we can use a consistent data frame format or CSV format. Okay. Now the language model, we can create our own validation set. And so you've probably come across by now sklearn.modelselection.trainTestFit, which is a really simple little function that grabs a data set and randomly splits it into a training set and validation set according to whatever proportion you specify. And so in this case, I concatenate my classification, training, validation together. So it's going to be 100,000 altogether. Split it by 10%. So now I've got 90,000 training, 10,000 validation for my language model. So go ahead and save that. So that's my basic, get the data in a standard format for my language model and my classifier. Right. So the next thing we need to do is tokenization. So tokenization means at this stage we've got, for a document, from a peer review, we've got a big long string, and we want to turn it into a list of tokens, which are kind of a list of words, but not quite, right? For example, don't, we want to be don't, we probably want full stop, be a token, so, right? So tokenization is something that we passed off to a terrific library called Spacey, partly terrific because an Australian wrote it, and partly terrific because it's good at what it does. We put a bit of stuff on top of Spacey, but the vast majority of the work's been done by Spacey. Before we pass it to Spacey, I've written this simple fix-up function, which is basically each time I looked at a different data set, and I've looked at about a dozen in building this, everyone had different weird things that need to be replaced. So here are all the ones I've come up with so far. Hopefully this will help you out as well. So I HTML and escape all the entities, and then there's a bunch more things I replace. Have a look at the result of running this on text that you put in and make sure there's not more weird tokens in there. It's amazing how many weird things people do with text. So basically I've got this function called getAll, which is going to go ahead and call getTexts, and texts is going to go ahead and do a few things, one of which is to apply that fix-up that we just mentioned. So let's kind of look through this because there's some interesting things to point out. So I'm going to use pandas to open our train.csv from the language model part. But I'm passing in an extra parameter you may not have seen before, so chunk size. Python and pandas can both be pretty inefficient when it comes to storing and using text data. And so you'll see that very few people in NLP are working with large corpuses. And I think part of the reason is that traditional tools have just made it really difficult to run out of memory all the time. So this process I'm showing you today, I have used on corpuses of over 1 billion words successfully using this exact code, right? And so one of the simple tricks is to use this thing called chunk size with pandas. What that means is that pandas does not return a data frame, but it returns an iterator that we can iterate through chunks of a data frame. And so that's why I don't say top train equals getTexts, because here is the thing getTexts, but instead I call getAll, which loops through the data frame. And actually what it's really doing is it's looping through chunks of the data frame. So each of those chunks is basically a data frame representing a subset of the data.
When I'm working with NLP data, many times I come across data with foreign text or characters. Is it better to discard them or keep them?
No, definitely keep them. And this whole process is Unicode, and I've actually used this on Chinese text. This is designed to work on pretty much anything. Yeah. Yeah, in general, most of the time it's not a good idea to remove anything. Like old-fashioned NLP approaches tend to do all this like lemmatization and all these kind of normalization steps to kind of get rid of, the lowercase everything, blah, blah, blah. But, that's throwing away information which you don't know ahead of time when it's useful. So don't throw it away. Okay, so we go through each chunk, each of which is a data frame, and we call getTexts. GetTexts is going to grab the labels and make ints. It's going to grab then the texts. And I'll point out a couple of things. The first is that before we include the text, we have this beginning of stream token, which you might remember we used way back up here. There's nothing special about these particular strings of letters. They're just ones I figured don't appear in normal text very often. So every text is going to start with XBOS. Why is that? because it's often really useful for your model to know when a new text is starting. For example, if it's a language model, right? We're going to concatenate all the texts together, and so it'd be really helpful for it to know, oh, this article's finished and a new one started, so I should probably like forget some of that context. Yeah. Ditto is quite often texts have multiple fields, like a title, an abstract, and then a document. And so by the same token, I've got this thing here which lets us actually have multiple fields in our CSV. Okay, so this process is designed to be very flexible. And again, at the start of each one, we put a special field starts here token, followed by the number of the field that's starting here for as many fields as we have. Then we apply our fix up to it. And then most importantly, we tokenize it. And we tokenize it by doing a process or multiprocessing, I guess I should say. And so tokenizing tends to be pretty slow, but we've all got multiple cores in our machines now, and some of the better machines on AWS and stuff can have dozens of cores. Here on our university computer, we've got 56 cores. SpaCy is not very amenable to multiprocessing, but I finally figured out how to get it to work. And the good news is it's all wrapped up in this one function now. And so all you need to pass to that function is a list of things to tokenize, with each part of that list will be tokenized on a different core. And so I've also created this function called partition by cores, which takes a list and splits it into sublists. The number of sublists is the number of cores that you have in your code. Okay, so on my machine, without multiprocessing, this takes about an hour and a half, and with multiprocessing, it takes about 2 minutes. Right? So it's a really handy thing to have. And now that this code's here, feel free to look inside it and take advantage of it through your own stuff. Right? Remember, we all have multiprocessing through cores even in our laptops, and very few things in Python take advantage of it as you make a bit of investment.
Did he say he was using the multiprocessing module for the?
So there's a couple of tricks to get things working quickly and reliably as it runs.
Did he say he was using the multiprocessing module to do the?
And so here's the result.
Sorry.
Did he say he was using the multiprocessing module for parallelism?
Yeah.
I think
Yeah,
so.
to use all the cores.
Yeah, he
It's
said
like
that.
tokenizing all the text.
Yes, he said spaCy didn't play nice with it, and so he had to do some things, but it's
Yeah,
abstracted from you through his library.
Yeah.
and then so that's all inside the guts of the FastAI.txt.
Yeah.
And then so when he goes, like the tokenizer, like I guess that was like I forgot.
I guess I can't scroll that. So.
It's like 34 or something. Yeah, in box 137, tokenizer. Where do you import that then?
Oh,
I
all the way
think-
to the top.
I think you called it
star
import star.
from his library.
Oh, I see.
Yeah.
Because he doesn't believe you should declare your imports.
I see.
It's just import star.
Okay. Then maybe I was getting those two confused then. Never mind. Okay, sorry. Minor detail.
So it was originally capitalized, right? But the interesting thing is that normally people either lowercase everything or they leave the case as is. Now, if you leave the case as is, then screw you, all caps, and screw you, lowercase, are two totally different sets of tokens that have to be learned from scratch. Or if you lowercase them all, then there's no difference at all between screw you and screw you. Right? So how do you fix this so that you both get the semantic impact of like, I'm shouting now, right? But not have every single word have to learn the shouted version versus the normal version. And so the idea I came up with, and I'm sure it's too, is to come up with a unique token to mean the next thing is all uppercase. So then I lowercase it. So now whatever used to be uppercase is now lowercase, it's just one token, and then we can learn the semantic meaning of all uppercase. Okay? And so I've done a similar thing if you've got like 29 exclamation marks in a row, we don't learn a separate token for 29 exclamation marks. Instead, I put in a special token for the next thing repeats lots of times. And then I put the 929, and then I put the exclamation.
Why didn't you try to put a special token for the uppercase? So this is using uppercase for every.
He's just like saving himself like memory. Because if he didn't have that, then like
And you
like
want to treat the same word as the same token also, both
Yeah.
uppercase or lowercase. But then you do want to somehow mark it that it was different at the same time.
Yeah, if it was different, then if you want to mark it, it's different. Then why
But it needs to be.
why can't you use
Yes.
uppercase for you versus
so you don't have to keep track of two different tokens. So like if somebody said like uppercase, all uppercase hello, and
Because
then
they
in
are the
another
same.
place it was like lowercase hello, you have to store both of those.
right?
Well, not only do you have to store it, but the machine learning model might only get 2 examples of all capital hello.
That's true too.
And then it wouldn't know that all lowercase hello is the same word. Because to them,
Really
it's
don't.
totally different tokens. Like, you know, one could be
But like
hello
if
and the
the
other
model
could be
was
plus.
essentially lowercasing everything, then it would notice that, right? I guess I'm missing.
Yeah, so if you lowercase everything, then it doesn't know that the original intent was to shout. Right, because you either lose.
He wants it, the model to know they're different yet the same. So the way to do that is to split it into 2 different tokens, one specifying that different, the other one is specifying that they're the same token.
You still have to use the T up, whatever.
Well, it's whatever you choose to.
Yeah, so like in here, I think it's like MGM or something.
Yeah, it's
Yeah.
down towards the lower right.
Oh,
Or
yeah.
MGM, it probably doesn't matter, but
Yeah. But
I feel like he's not saving himself. Like you're adding another T up, which is you could add a capital.
I don't think it's saving them.
No, I don't think the memory thing
or even
is
like
compelling.
saving
It's
the encoding scheme. Maybe I'm missing.
I think it's a matter of you want to give the machine learning model as many examples as you can of every single word in your corpus, right?
Right.
And so if you took half of your words and you split them into like capitalization schemes, like these are capitals and these are lowercase, those are totally different bit configurations, right? They're totally different tokens. They're totally different numbers.
Right.
Whereas they mean the same thing. They're just one is the emphasized version of the other. And so he wants to keep the fact that they're the same thing with just emphasis difference by adding, like pulling the emphasis into a separate token.
I see. So we'll have like, well, maybe down below later, we'll talk about like the inputs being, you know, the token with the emphasis. It's 2 separate input features.
Yeah, I don't know. I'm trying to come up with an example where an emphasis would actually make a difference, but
Maybe he'll explain later in the video as it goes down. I guess I might.
like you could imagine reading
here.
yourself a technical manual,
Uh-huh.
and you saw this new word that you've never seen before, but you only saw it twice, and so you couldn't tell just from that sentence what the context was. And then you saw another word, and if like you saw it in a different context, you would know immediately what it was. But because they were only different through the capitalization, instead of you noticing that, you would think they're totally different, right? Because they capitalized a different letter. It's a totally different word. So it just gives the model more opportunities to learn like the semantic meanings of words.
Do not, but with the apostrophe instead.
so part of the tokenization is like they take words that are just because don't is just like do not.
Why
put
not
together,
replace it with not then?
Still thoughts.
I think that's just how they do the token.
Even if it's the same thing as do not. Just replace it.
I'm sure they could.
Yeah,
I don't. Yeah.
They're coming down on the other side.
Yeah.
But in apostrophe T and in OT mean the same thing, but they're different.
Yeah.
Yeah, so I don't know.
Yeah. I think. Yeah,
They
because
should
I
have just
know,
put a thing
I
on
know,
the front
like,
of the word that
yeah.
says this is a contraction of these two words.
And then put it.
yeah,
Contraction, and then do not, and should not.
yeah.
Reproduce it later.
And I think
But
there's,
Spacey already
yeah.
did that part, so he didn't do
Yeah.
that part. So he probably just didn't dig into it.
and I think the reason that it's like that too, it's like I don't think it says, oh, this word is don't, split it into do and not. I think it's saying there's an apostrophe here that's in a certain part of the word. So I'm just going to split it based on some like predefined rule. If that, so like can't and don't, like it doesn't make the distinction that it's like, or I guess, is there any N apostrophe T that it doesn't stand for not, it stands for something else?
Well, they do an apostrophe S down there on the possessive. So Garland S own writing,
Where,
almost at the bottom on the left. Yeah. Just,
oh, here. Yeah, I think it, yeah.
Then at the top, like if you go 1, 2, 3, 4, 5, 6, 7, 8, 10 lines up,
That's
one line below.
That's the do not I was talking about. Yeah.
Yeah,
That's
yeah.
weird.
Yeah, I think, yeah. Maybe it's just easier somehow. I don't know. Because, yeah, it is weird. It's like they're doing the opposite thing that he was just trying to do with the uppercase letters. Although, I don't know, like, knowing that it was don't, but if you're not, could potentially tell you something.
yeah, it's a
Don't is more
formal
slangy
versus
or something.
informal,
Yeah.
But you would imagine if you really wanted to pull out the emphasis sort of from the meaning, you'd have a contraction
Yeah,
first word, second word instead of
that's true. Yeah.
doing it.
Maybe that was just too much work or
Yeah.
something. I don't know. Yeah. All right.
And so there's a few little tricks like that. And if you're interested in LP, have a look at the code, the tokenizer, for these little tricks that I added. Because some of them are kind of fun. Okay, so the nice thing with doing things this way is we can now just np.save that and load it back up later. Like we don't have to recalculate all this stuff each time, like we don't have to do torch text or a lot of other items. Okay, so we've now got it tokenized. The next thing we need to do is to turn it into numbers, right, which we call numericalizing it. And the way we numericalize it is very simple. We make a list of all the words that appear in some order, and then we replace every word with its index into that list. The list of all the words that appear, or all the tokens that appear, we call the vocabulary. So here's an example of some of the vocabulary. The counter class in Python is handy for this. It basically gives us a list of unique items and their counts. Okay. Here are the 25 most common things in vocabulary. We can do things like apostrophe S, double quote, and then the paragraph, and also stuff like that. Now, generally speaking, we don't want every unique token in our vocabulary. If it doesn't appear at least 2 times, then it might just be a spelling mistake or a word. I mean, we can't learn anything about it, it doesn't appear that often. Also, the stuff that we're going to be learning about, at least so far on this part, gets a bit clunky once you've got a vocabulary bigger than 60,000. Time permitting, we may look at some work I've been doing recently on larger vocabularies, otherwise that might have to come in future course. Okay. But actually, for classification, I've discovered that doing more than about 60,000 words doesn't seem to help. So we're going to limit our vocabulary to 60,000 words, things that appear at least twice. And so here's a simple way to do that. Use that dot most common, pass in the max vocab size. That'll sort it by the frequency, by the way. And if it appears less often than a minimum frequency, then don't bother with it. Okay. So that gives us either S, that's the same name that torch text used. Remember, it's int to string, but this is just the list of the tokens, unique tokens in the vocab. I'm going to insert 2 more tokens. a token for unknown, a vocab item for unknown, and a vocab item for cat. Okay. Then we can create the dictionary, which goes in the opposite direction, so string to int. That won't cover everything because we intentionally truncated it down to 60,000 words. Right? And so if we come across something that's not in the dictionary, we want to replace it with 0. So we can use a default dict for that with a lambda function or a string. Okay, so you can see all these things we're using to kind of keep coming back up. So now that we've got our S2I dictionary defined, we can then just pull that for every word for every sentence. Right? And so there's our numericalized version, and there it is. Okay? And so, of course, the nice thing is, again, we can save that step as well. Right? So each time we get to another step, we can save it. And these are not very big files compared to what you're used to with images. Text is generally pretty small. Very important to also save that vocabulary, right? Because this list of numbers means nothing unless you know what each number refers to, and that's what HOS does. Okay, so you save those 3 things, and then later on you can run them. Okay. So now our vocab size is 60,002, and our training language model has 90,000. Okay. So that's the pre-processing we do. We can probably wrap a little bit more of that into the utility functions if we want to, but it's all pretty straightforward, and basically that exact code will work for any data set you have once you've got it in that CSV format. So
each word is a number now, right? But so what about the previous tokens, like apostrophes, commas, those things?
Yeah, so those all
Those
now
become
map
number
to a
two.
number.
Okay.
Yeah.
And uppercase. But uppercase word, say uppercase hello and lowercase hello, will have the same number.
Right.
Yes.
But just before that, there will be another number
token.
to say, okay.
So I guess you have to have basis is now going to be based on 2 n-grams or something. Whatever the see things 2 words at a time to make a correlation.
Yeah, so he'll talk about it later, but I think he's doing like 70 word anagrams for the language model.
Yeah,
portion.
so he's going to train a recurrent neural network.
70.
Give them 70 words at a time.
Yeah.
They predict the 71st word, and then he trains it on the purpose to do this language model, and then he takes that as the thing to do transfer learning on. Like that's the base model that then uses to do the other task.
Yeah. How much time do we have? 10 more minutes.
Here is a kind of a new insight that's not new at all, which is that we'd like to pre-train something. Like we know from lesson 4 that if we pre-train our classifier by first creating a language model and then fine-tuning that as a classifier, that was helpful. Remember, it actually got us a new state-of-the-art result. We got the best IMDb classifier result that had been published, but quite a bit. Well, we're not going far enough, though, right? Because IMDb movie reviews are not that different to any other English document, compared to how different they are to a random string or even to a Chinese document. So just like ImageNet allowed us to train things that recognize stuff that kind of looks like pictures, and we could use it on stuff that's nothing to do with ImageNet, like satellite images. Why don't we train a language model that's just like good at English, and then fine-tune it to be good at movie reviews? So this basic insight led me to try building a language model on Wikipedia. So my friend Stephen Merity has already processed Wikipedia, found a subset of nearly, the most of about throwing away the stupid little.
His insight was to take pre-trained models on English and then apply it to the IMDb data set.
Yeah.
Okay.
Articles, for most of the bigger articles, and he calls that Wikitext 103. So I grabbed Wikitext 103 and I trained the language model. And I used exactly the same approach I'm about to show you to train the IMDb model. Instead I trained the Wikitext 103 language model. And then I saved it and I've made it available to anybody who wants to use it at this URL. So this is not a URL for Wikitext 103, the documents. This is the Wikitext 103, the language model. And so the idea now is let's train an IMDb language model which starts with these ones. Now hopefully for you folks, this is a extremely obvious, extremely non-controversial idea because it's basically what we've done in nearly every class so far. But when I first mentioned this to people in the NLP community, I guess like June, July of last year, there couldn't have been less interest. I asked on Twitter, where a lot of the top Twitter researchers are kind of people that I follow and they follow back. I was like, hey, what if we like pre-trained like a general language model? No, well, language is different, you can't do that, or like, I don't know why you bother anyway. I've told people at conferences, and, pretty sure people have tried that, it's stupid. Like, there was just this like, I don't know, this weird like, straight pass. And, I guess because I am, arrogant and vociferous, I ignored them. They know much more about NLP than I do and just tried it anyway. And let me show you what happened. So here's how we do it, right? Grab the Wikitext models, right? And if you use wget -r, it'll actually recursively grab the whole directory. So a few things there. We need to make sure that our language model has exactly the same embedding size, number of hidden, and number of layers as my Wikitext one did. Otherwise, we can't load what's in. Okay, so we can run this here. So here's our pre-trained path. Here's our pre-trained language model path. Let's go ahead and torch.load in those weights from the forward Wikitext 103 model. Okay. We don't normally use torch.load, but that's the PyTorch way of grabbing the file. And it basically gives you a dictionary containing the name of the layer and a tensor of those weights, or an array of those weights. Now here's the problem. That Wikitext language model was built with a certain vocabulary, which was not the same as this one was built on. Right? So my number 40 was not the same as Wikitext 103 model's number 40. So we need to map one to the other. Okay? That's very, very simple because luckily I saved the I2S for the Wikitext vocab. Right? So here's the list of what each word is when I'm training the Wikitext 103 model. And so we can do the same default dict trick to map it in reverse. Right? I'm going to use -1 to mean that it's not in the Wikitext dictionary. And so now I can just say, okay, my new set of weights is just a whole bunch of zeros with vocab size by embedding size. So we're going to create an embedding matrix. I'm then going to go through every one of the words in my IMDb vocabulary. Right? I'm going to look it up in S to I2, so stream to int with the Wikitext 103 vocabulary and see if that word's there. Okay? And if that is word there, then I'm not going to get this -1, right? So R will be greater than 0. So in that case, I will just set that row of the embedding matrix to the weight that I just looked at, which was stored inside this named element. And so these names, you can just look at this dictionary, and it's pretty obvious what each name corresponds to. It looks very similar to the names that you gave it when you set up your module. So here are the encoder weights. Okay. So grab it from the encoder weights. If I don't find it, then I will use the row mean. In other words, here is the average embedding weight across all of the Wikitext ones. Okay, so that's pretty simple. So I'm going to end up with an
average.
So
It's the average.
So I think he's not doing.
Find it, he sets it to the average of all.
Yeah, I
Well,
think he's
encoding.
not doing like the standard transfer learning where you start with the fully trained weights and then you just fine tune from the end. I think instead he's starting with a randomly initialized new network, but then he's carrying over the embedding layer from his other network. And so he carries it over one token at a time. And then any tokens that he finds that are new that weren't in his other one, they just get the average embedding values. And so, and then he's gonna use that as a starting point to train anyway. So they're gonna learn their values later for those new words. They just get, instead of starting out random, they start out average.
Yeah.
The average right there. That's else.
Yeah, I don't know why it's not just like let it be randomly.
I think he just said it was more stable to start with. I think he might actually talk about it in a few seconds.
embedding matrix for every word that's in both my vocabulary IMDb and the Wikitext 103 vocab. I will use the Wikitext 103's embedding matrix weights. For anything else, I will just use whatever was the average weight from the Wikitext 103 embedding matrix. Okay, and then I'll go ahead and I will replace the encoder weights with that turned into a tensor. We haven't talked much about wait time, we might do so later, but basically the decoder, so the thing that turns the final prediction back into a word, uses exactly the same weights, so I pop it there as well. And then there's a bit of a weird thing with how we do embedding dropout that ends up with a whole separate copy of them for a reason that doesn't matter much. Anyway, so we just pop the weights back where they need to go. So this is now something that a dictionary we can now, or a set of torch state which we can load in. So let's go ahead and create our language model.
And maybe he didn't talk about it. I don't know, that seems like a good stopping spot maybe.
I thought WGTS were the weights he was getting from his language model to be trained. Yeah, you can't just scroll up.
There.
Yeah.
Yeah, so he's getting it from the pre-train.
Yeah, so that's WGTS is something he's loading in from somewhere else.
Yeah, I think that's the dictionary with all the weights.
And then he's assigning to it.
Yeah, I think he's just overwriting. So he's like replacing just some of the layers with like the new layers that he's creating. Like with like the
So his
like the
encoder is
medium.
going to be identical to his decoder weights?
I don't
Okay.
think so. Which part of you?
Well, those 3 lines in line 41.
To begin with, I guess.
Yeah, he's saying that encoder.weight is the tensor version of new W. And then decoder weight is also the same thing.
But he's copying it because it's going to change later.
Yeah, so he gets separate tensors. They're not the same tensors,
Yeah.
but they have the same values.
Yeah, maybe that's the weight tying thing he was talking about.
Yeah.
I don't know. Like I kind of skipped over those 3 lines.
Did you do all this stuff in yours?
I did, yeah. I didn't have to change this portion of it.
Yeah.
Like I essentially, if it worked for what I needed to do, I didn't really worry about what the wait time was.
So you didn't
But-
train a model on Wikipedia. You went ahead and used his.
I did. Well, yeah, because I didn't train it on Wikipedia myself.
Okay.
I loaded the same one that he loaded in.
Okay.
And then instead of training it on the IMDb reviews, I trained it on a Twitter corpus instead. So yeah, it was literally like all the same steps. I had to do like a few tweaks here and there, and I changed the variable names to something less insane where I could. But yeah, other than that, like you'll see, it's like very similar to what he has.
What was your objective? What was your achieve?
So I was classifying like celebrity tweet sentiments. So I just thought it could be an interesting project because I wanted to try this whole thing out and do like a mini blog post about it.
Who was the happiest celebrity?
I think it was like Jeff Bezos or something. Bezos.
Yeah.
Yeah, actually.
Did you add a token or hashtag? Because in Twitter.
Oh yeah. Did you?
I did. So there were a lot of. I didn't look too closely, but there's a lot of unknowns. Most of them are emojis. I didn't actually check for hashtag. I've heard like this was not the most careful analysis in the world.
It sounds like you've went enough appetite for next lecture.
Yeah.
I forget what. Oh yeah, I was gonna see who was the most. Yeah, Jeff Bezos.
Our supreme overlord, Jeff Bezos.
Yeah, or actually, I think he tied with Justin Bieber. So.
The modern day Rockefeller.
Yeah. Which was interesting because Bill Gates was way more negative. But I think it's because Bill Gates tends to tweet about stuff.
Yeah. About the whole actual world.
Yeah.
So I was in the news recently. Apparently, I resigned my position as the chief financial officer